Alright folks, this is the last slide, last show from slideshow from section 7.3, the sampling distribution of the sample mean. So we've looked at how the sampling distribution of the sample mean is affected by population and standard deviation. We figured out that that the mean of the sample means is equal to the population mean, and that the standard deviation of the sample mean is equal to the standard deviation of the variable under consideration divided by the square root of n. So we've learned those two bits of information. Now it's time to look at what happens in terms of normal distribution. Okay, so a sampling distribution of a sample mean for a normally distributed variable. Suppose that the variable x of a population is normally distributed. Then for samples of size n, the variable x bar, or the sample mean in this case, is also normally distributed. Okay, it has a mean of mu and the standard deviation of that formula there. So here is our first problem. Okay, sampling distribution of the sample mean for a normally distributed variable. Consider the IQ, which is normally distributed with a mean of 100 and a standard deviation of 16. Obtain the sampling distribution of the sample mean for the sizes of 4 and 16. Alright, so what's the population? Letter A. What's the population? What is the mean of the sample mean? What is the mean of the sample mean? Well, hopefully you're screaming at the screen, because hopefully you realize it's 100 since the mean is 100 here. Remember, they're one and the same. So what's the mean going to be over here? The mean of the sample mean is still going to be 100. It doesn't matter that sample size increases, that mean still stays the same. Alright, well, what about the standard deviation? Now this is where we have to use our formula. Okay, so we know that our sample size is 4 here, so we know it's the square root of 4. They gave us the standard deviation in the problem of 16. So 16 divided by the square root of 4 should give us a standard deviation of 8. So it's normally distributed with a mean of 100 and a standard deviation of 8 when you have a sample size of 4. When you have a sample size of 16, it's normally distributed, but it has a mean of 100 still. But what differs is the standard deviation. When you have a sample size of 16, we're taking the square root of 16 on the bottom, and so we essentially, with this particular problem, we cut our standard deviation in half. So notice, it's still normally distributed, it still has a mean of 100, but the standard deviation shrunk because our sample size grew. Standard deviation shrunk because our sample size grew. Now the central limit theorem basically says this: if you have a large sample size, the variable x bar is normally distributed regardless of whether x is normally distributed. So in other words, it doesn't matter whether your initial distribution is normally distributed. If you have a large sample size, the variable x bar is always going to be approximately normally distributed no matter what. So the approximation becomes even better as you increase sample size. So in summary, suppose that the variable x of a population has a mean and a standard deviation. Then for samples of size n, the mean of the sample mean equals the population mean. Okay, we've said that. The standard deviation equals the square root of the standard population standard deviation divided by the square root of the sample size. Alright? If it's normally distributed, if x is normally distributed, then if x is normally distributed, then so is x bar, regardless of the sample size. Okay? If x is normally distributed, so is x bar. And if the sample size is large, then x bar is going to be approximately normally distributed no matter whether x is or not. Okay, regardless of whether x is. Alright, so here's our graphical proof. Notice here's a normal distribution, the first one here. Notice all of our samples are still normally distributed. And notice as the sample size increases, our standard deviation decreases. So this little dotted line here, this is the mean. So notice how it's getting, the blue line's getting closer and closer to the mean. So as you increase sample size, the standard deviation is decreasing. These last two, this one especially in particular, the one in the middle here, notice it's not normally distributed. But notice what happens. As we increase sample size, notice it works its way to an approximate normal distribution. Same thing on the last one here. Even though it's not normally distributed, it is working its way toward a normal distribution. It is working its way toward a normal distribution. Okay, so that's just reaffirming what I just told you, the summary there. So here we're going to put it all together. Now this is going to be really, theoretical. Okay, so bear with me through this. I'm stretching your brain a little on this one. The National Center for Health Statistics publishes information about birth weights. According to the document, birth weights of male babies have a standard deviation of 1.33 pounds. Determine the percentage of all samples of 400 male babies that have birth weights within 0.125 pounds of the population mean. Okay, of the population mean. Okay, so interpret your answers in terms of sampling error. All right, so first things first. We know that the mean of the sample mean is going to equal the mean of the population. Now, in terms of the standard deviation of the sample mean, that's going to be our 1.33 divided by the square root of 400, which is 0.0665. So, once that happens, I want you, because we have such a large sample, okay, the larger the sample, remember, the more it's going to be normally distributed. So think about this as a normally distributed variable. Okay, we want to think about this as a normally distributed variable. So remember, our mean would be in the middle. So what we essentially are wanting to know is we are wanting to know what's the percentage within 0.125 of the mean. So essentially what I'm saying here, when I'm talking percentage, what I'm saying is this area right here under this curve. This goes back to section 6.1. What is this area under the curve in terms of percentage? That's all this is. That's all this is. What's the area under the curve in terms of percentage? Because that will tell us, if you find out what the area is from each end, from where it's less than 1.25 and greater than 1 by 0.125. If you find that shaded area, that will give you the percentage of those babies that is that's within that area. The area under the curve will. Now, again, it's only because we have a large sample size that we know this is going to be somewhat normally distributed, approximately, okay? So, what's the first thing we have to do to find that area under the curve? Well, we have to change our problem to a z-score. We have to change our values to z-scores. So remember what our z-score is. Our z-score is our x value minus the mean over the standard deviation. In this case, my x value is going to be mu minus 0.125 minus mu all over our standard deviation, which is 0.0665. And then our other one will be, our other z-score will be plus 1.125 minus the population standard deviation, all over the sample standard deviation. Population mean is what I meant to say a moment ago. So here, this would be our two z-scores. So notice, these two are going to cancel each other out. So notice what we get here. You should get a negative 1.88 for this z-score and a 1.88 for this one. So this is negative 1.88 in terms of z-score and a 1.88. Okay? So what you need to do is you need to find the area under the curve between those two z-scores. So remember how we do that. It's all the area to the left of 1.88 subtracting the area to the left of negative 1.88. So you need to turn back in the back of your book like we did in Chapter 6. Turn to Table 2 in the back of your book and find that area in between there using Table 2. Table 2 in the back of the book. Okay, find that area. And when you do that, that area underneath here, if you do this correctly, should be 0.9398. So you're going to go, remember what we're trying to do. Go back to Chapter 6 if you have to. When you're finding the area in between, remember it's the area to the left of 1.88 minus the area to the left of negative 1.88. So what you need to do is go find 1.88 on your table 2, scroll over and look and find the area in the middle of the table that is equal to 1.88. Find the area that's equal to negative 1.88. Subtract them. And if you do that, you should get 0.9398. Now, why is that of significance? Because we can change that back to the percent we were wanting originally in the problem. So that's 93.98%. 93.98%. So, how do we interpret this? Well, about 94%. There's about 94% chance that the sampling error made in estimating the mean weight of babies lies between 0.125 and negative 0.125 from the mean. Okay, so 94% of all male babies that of a sample of 400 male babies will be at most 0.125 above or below the mean. 94% of all the samples of those 400 will be above and below the mean by 0.125. So it's basically saying that 94% will be in this range. Now, like I said, this is a real theoretical problem. Hopefully you understand how we got to where we did with it. If not, rewind it, watch it again. It'll make sense to you. I would also go back and watch the Chapter 6 videos where we found the areas under the curve. I think it'll help make more sense to you there as well. If you have questions, feel free to ask your instructor. I hope this helped somewhat at least. Y'all have a great day.